Good morning, everyone. Thank you for joining us today. I'm sorry for that slight delay. There was a technical issue that's now been resolved, so hopefully now everything will run smoothly. Welcome to this latest installment of the Eupraxia Virtual Seminar Series. Today we are kindly joined by Dr. Aaron Liberman, who is a researcher at the Weizmann Institute of Science, where he works on laser-wakefield acceleration. His seminar today is titled Towards Dephasingless LWFA, and will cover recent studies and results on manipulating a laser's space-time structure to overcome the dephasing limit and achieve higher electron energies. If you would like to ask a question, please use the Q&A function, which can be found at the top bar of the screen. You can submit these at any point during the seminar, and we will put these to Aaron at the end of the presentation. Thank you once again for joining, and I hope you enjoy the seminar. So whenever you're ready to begin, Aaron, over to you.
So thank you very much. Again, apologies for the technical snafus. I'm Aaron. I'm from the group of Victor Malka at the Weizmann Institute. I just finished my PhD, and I'll talk to you today about the work that we're doing trying to realize dephasingless laser-wakefield acceleration. A quick overview, I'll just briefly go over the need for high electron energy laser-wakefield acceleration. I'll talk about the dephasing limit, which is the challenge that we're trying to overcome. Our proposed solution, which is structuring light in the near field using spatiotemporal couplings, and in the far field using an X-ray parabola, and our experimental results to date. And then I'll just do a kind of a small shift and talk about a new spatiospectral measurement device that we developed together with the LOA in France. So laser wakefield acceleration has many uses and has many great achievements. But a few applications I think are particularly interesting for the need to push to really high electron energies are, for example, the idea of developing compact X-ray free electron lasers using laser wakefield accelerators. So there was this great result published in 2021 in Nature on free electron lasing at 27 nanometers. And that's an important achievement, but of course 27 nanometers is kind of just on the precipice, but we want to go to 1 nanometer or even to angstrom level photons. So for that, we need to go to higher electron energies because the FEL wavelength scales inversely with the square of the electron energy. This particular result was with 500 MeV electrons. So if we want to go to the sub-angstrom regime, we're talking about 10 GeV or more electrons. Another interesting application is kind of QED, strong field QED studies using LWFA. So there was this proof of concept paper on all optical nonlinear Compton scattering. Also, fantastic results. And there, the quantum nonlinearity parameter, meaning how strong of a quantum QED, strong field QED effect you see, also scales with the square of the electron energy. In their particular result, they used electron energy about 2.5 to 3 GeV, and their quantum nonlinearity parameter was 0.32, so below 1. So they're starting to see some effects of strong field QED, but not really in the strong field QED regime. So for that, again, we want to push the electron energy higher in order to really probe some very interesting physics. What's the state of the art today? So the state of the art today is about 10 GeV electrons from this great result from the Berkeley group, where they use a plasma channel. So they use one laser pulse focused by an axicon to create a plasma channel, and then they fire their main laser through this plasma channel in order to mitigate beam diffraction. They had about a 30 centimeter long accelerator, and they were able to achieve, depending on the laser parameters and the gas parameters, but at their best, they were able to achieve electron energies with a tail that extended into 10 GeV. But what if we want even higher electron energies? Well, already here we see one of the challenges, which is beam diffraction. But perhaps there's even more nefarious of a challenge, which is the dephasing limit. And essentially, it's the problem that relativistic electrons outpace the laser in plasma. So I'll begin with the electrons in the accelerating phase of the bubble being Coulomb repulsed by the back of the bubble. After a certain amount of acceleration, the electrons move relative to the bubble, cease to be accelerated, and can even move into the decelerating phase of the bubble where they're actually slowed down. And our solution is that we want to speed up our laser driver in order to speed up our bubble. so that we can phase lock the electrons with the bubble, keeping them constantly accelerating. And there have been several works which have shown huge potential upside to realizing these dephasingless schemes. So if we wanted to dream ridiculously big and talk about tera-electron volt electrons, well, with a conventional RF accelerator, we need about 10 kilometers, at least 10 kilometers of acceleration length in order to achieve TeV electrons. We're talking about a multinational, multi-billion-dollar machine. But for those for whom 10 kilometers is, let's say, a big number, in Weizmann terms, it's about the distance between Weizmann Institute and the beach. Again, a large machine. We're not that close to the beach, unfortunately. Traditional non-dephasingless laser wakefield accelerator, we need about 200 meters of plasma in order to achieve TeV electrons. Again, in Weizmann terms, it's the distance between the physics building in the blue dot and the lunch hall. Now, that may not be that long of a distance to walk for lunch, but to keep an ultra high intensity laser pulse focused and accelerating over that distance is an enormous feat. But if we can crack true dephasingless acceleration, we'd only need about 4 meters of plasma to achieve TeV electrons. Now that's about the length of our lunch, our coffee setup when we all get together as a group. And the thing is that meter scale guiding and acceleration is something that we're actually starting to be able to do. So if we can crack dephasingless acceleration, while not currently feasible with today's technology, it's at least relevant to talk about in the next, let's say, 2 decades, achieving TeV scale electrons. And that's the reason why we're pushing towards this dephasingless acceleration. So how do we do it? Well, as I said, the first thing that we do is we turn towards spatiotemporal couplings to structure our light in the near field. Spatiotemporal couplings, they're basically spatially dependent chromatic aberrations. So if we think about a pulse in frequency space, we have a Gaussian frequency envelope. We add a phase term, which couples space and frequency in a way that cannot be decoupled into a separate spectral phase and a separate spatial phase. So we think about the fact that ultra-short laser pulses naturally are broadband. And now we don't just think that they have many colors, but we also think that each of these colors has a wavefront. And when we go through a chromatic optic like a singlet lens, we can actually have, for example, different curvatures to the different wavefronts. So here we have an effect which is both spectrally dependent and spatially dependent at the same time. Now we call them spatiotemporal couplings because we typically think about the effect in the temporal domain. So here before we had a laser pulse which was traveling uniformly in time. And after focusing, we now have a radially dependent pulse delay. This particular one is called pulse front curvature. It'll be important to us later on, but it's part of the general family of spatiotemporal couplings, which give us spatially dependent pulse delays and spatially dependent pulse durations. But just the near field manipulation is also not enough. We need to actually change the way that we focus the pulse. And for that, we turn to the axiparabola. Now, to understand the axiparabola, let's just remind ourselves about the parabolic mirror, which has the nice mathematical property of focusing all annular segments of the beam to the same mathematical point on the optical axis at its focal length. The axiparabola, by contrast, it focuses different annular segments of the beam to different points along the optical axis. We can think of it as a parabola with a controlled amount of spherical aberrations. Now, as before, we have a focal length, we call it the nominal focal length, but we also have a focal depth, which is basically the length over which we've smeared out our focal line. Now, in addition to changing the location to which intensity is focused along the optical axis, the axiparabola also introduces a different dynamic with which intensity is focused along the optical axis. We've changed the geometry of the optical path lengths, so we've actually changed the timing between the focusing of this annular segment and this annular segment and this annular segment. So now we can think about the velocity with which the focus propagates along the optical axis. Again, each individual ray is always traveling at the speed of light in that medium, but the focus now propagates at a different velocity. And it turns out that for the axiparabola is relevant to us, the ratio between the velocity of focusing and the speed of light is 1 plus a positive number. So it's actually a superluminal appearance velocity naturally just from the geometry of the accelerators, which makes this a particularly interesting candidate for speeding up our laser driver. But again, just the accelerators is not enough. So here we have a flat pulse focused by an accelerators, and we're given 3 snapshots of a laser wakefield accelerator. The green is the laser driver, the blue to red is the accelerating to decelerating phase of the bubble, and the yellow are the injected electrons. And we see that at time 0 when we begin the acceleration, the electrons are in the accelerating phase of the bubble. But by the time we've ended the acceleration, the electrons are fully dephased and being decelerated. But if we properly sculpt our laser pulse using spatiotemporal couplings before focusing, we can play with this propagation velocity, and we can keep the electrons constantly phase locked with the bubble and constantly accelerating. So this was the theory, and what we wanted to start doing was to start seeing what parts of this can we actually implement experimentally. So the first thing that we did is just we optically started with, can we actually measure and manipulate the propagation velocity using spatiotemporal couplings and the accelerators? So for that, we needed to develop a measurement device which can resolve this. And what we did is we passed our beam through 2 specially designed masks, which together pass through a central reference beamlet and a radially and angularly offset test beamlet. These 2 beamlets are then reflected off of a segmented mirror, where the central part of the mirror is on a piezo. So we can actually change the delay between the reference beamlet and the test beamlet. They're then focused by the accelerators, and this interference is imaged. Now, as we do a delay scan, we get a series of fringe patterns. And the fringe patterns are basically a measure of the synchronization of the beamlets in time. So as the beamlets become more synchronized, we have a stronger fringe contrast. And as the beamlets become asynchronized, we lose our contrast. So if we create a map, we can find the point of maximum contrast. And that's the point of synchronization between the 2 beamlets. And knowing how much delay we had to add or take away in order to get to that point of synchronization gives us the relative arrival time of that segment of the annular ring of the accelerators with the central reference beamlet, which we can think of as luminal propagation. And doing this for the different rings of the accelerators by choosing different radial holes gives us a map of the arrival time of the different radial segments. And if we take a derivative of that map, we can get the propagation velocity. We didn't just want to measure the velocity, though. We also wanted to change it using pulse front curvature. So inside of our beam, we actually have refractive beam expanders. And the first thing to note is just that the refractive beam expanders actually give you a natural pulse front curvature to the beam. Inside of our last beam expansion stage, we put a specially designed doublet lens, which was designed to not add other terms to the beam, but to change its pulse front curvature. And the effect that the doublet gives scales with the beam size. So as we move it inside of the telescope, its effect changes. So based on its position inside the telescope, it was designed to partially suppress, fully suppress, or invert the natural pulse front curvature that we get from our beam. So this is just the measurement of the pulse front curvature as a function of the doublet. So with no doublet, again, we have this natural negative pulse front curvature. As we introduce the doublet, we get a suppression of that curvature, and then eventually an inversion of the curvature into positive pulse front curvature. And this is the measurement of the accelerators velocity. So here on the x-axis, again, we have different doublet positions. And on the y-axis, we have a deviation from luminal propagation velocity. Positive here is superluminal, and negative is subluminal. So the natural negative pulse front curvature in our beam gives us a more superluminal propagation velocity. And then as we kind of suppress the pulse front curvature, we get into the luminal and then subluminal. Now, just with pulse front curvature, actually with the accelerators, your velocity is not constant. So here we're specifically measuring the initial deviation from luminal propagation velocity, but for each of these terms, there's a linear increase of the velocity as you go along the focal depth. Now that we've measured the velocity, it would seem to be that we were pretty close to the end of the problem, because we say, okay, we have measured velocities in a vacuum. we know the effect that the plasma should have on the propagation velocity. So now we can simply add that effect of the plasma onto our measured results, and then we'll know how quickly, the focus and therefore the bubble propagates. And now we can easily match it to the electron velocity inside of the bubble. So it turned out that this was pretty false assumption. And here is a good example of why. So if we take just two of the pulsar curvatures, a positive and a negative one, and we just add analytically the effect that we should have from a certain plasma density, then we get this line. On the x-axis, we're going along the focal depth. And on the y-axis, we have the accumulated shift from luminal propagation. So both of these are subluminal because now we've slowed down because of the effect of the plasma. But as you can see, again, as expected, the negative pulsar curvature is faster propagating than the positive. Now, what we did is we compared this to actually doing a simulation with these same conditions and measuring the 0 point of the electric field inside of our bubble. And it's very off. We do generally have the trend that the negative pulsar curvature is slightly faster than the positive, but the difference is really not what can be pushed analytically. And that's because of the fact that we have different rays coming in and they ionize at different points and travel through different amounts of plasma. And the bubble size is also modulating over the course of the acceleration. Many challenges that we'll see further on in this talk. And all that together means that there's a lot more work that needs to be done in order to actually get a stable, smooth velocity of propagation at the right velocity that we think. And so we understood that we have to do a lot more work. So what we did is then said, okay, we need to understand what's going on inside of this bubble. How does it behave? In order to start figuring out how to optimize this and how to get the difference, the delta between what we think should happen and what's actually happening to be as small as possible. So we turned to a technique called femtosecond relativistic electron microscopy, which was a technique largely developed in our lab. And what it allows us to do is to take snapshots inside the wake field with micron scale spatial resolution and near femtosecond scale, about 8 femtosecond scale temporal resolution. The experimental setup is that we have our beam, which is focused by the axis parabola and generates our flying focus wake field. We then have a second beam, which is temporally and spatially synchronized with the first, which is focused by a parabola onto another gas jet and accelerates an electron bunch. This electron bunch is then allowed to spatially expand before hitting the first wake field. The very intense fields inside of the wake field give momentum kicks to these probe electrons, which after further free space propagation turn into density perturbations, which can then be imaged on a scintillating screen. So just before I show the actual results, this is just the evolution of just a focal spot of the axis parabola, the focus focal spot over the focal depth. So you can see that because we have this Bessel-like beam at focus, we actually have a lot of dynamics, even just optically. And we'll see that the same is true inside of the wake field. So this is a snapshot at the beginning of the wake field formation. On the top, we have the actual experimental FREM image. In the green on the middle, we have a simulated reconstruction of this FREM image. And on the bottom, we have the simulated wake field, which would give us this simulated FREM image. And up until now, if you are familiar with these FREM images, you would say that this actually is not very different than a standard parabola focused wake field. And even if you look at the simulated wake field itself, it looks not that exotic. But if we just move 1 millimeter inside of the wake field, we see that the structure entirely changes. In the FREM image, we have the development of this dominant V-shaped structure, still periodic, but looking very, very different. And we have in the actual simulated wake field, we have the shrinking of the on-axis wake field and the development of the very strong radially offset wakes. So there is a lot of dynamics over the course of the acceleration itself. And again, this is something that further needs to be understood and needs to be taken into account in order to use these wake fields effectively. One nice thing that we found was that in regular FREM, the periodicity of the friend structures that we see is also a direct measurement of the density of the plasma. So it kind of gives us also for free an in situ density measurement. And what's nice here is that the periodicity of the friend structures that we see is actually the same. So we still maintain the ability to have an in situ density measurement, even though things are evolving over the course of the acceleration. But we were also able to start answering some questions which were relevant to us. For example, we can now change the pulse friend curvature and therefore the propagation velocity. But does this actually change the structure of the wake field, at least in the values relevant to us? So we took two images, one with a slightly negative pulse friend curvature, one with a more positive. And what we see now, the images look very different in terms of brightness, but that's shot-to-shot fluctuations of the electron beam. But actually, structurally, if you were to compare them, they're almost identical. In the simulated frame images, we see the same thing. On the top, we have the negative, on the bottom, the positive pulse friend curvatures. But here we see that, again, structurally, they're basically the same. Now, what's nice is that in the simulation, we also have an absolute reference frame. And therefore, we can actually see that the negative wake field is propagating faster, meaning it's actually spatially shifted than the positive one. So we see the difference in the velocity of propagation, but structurally we see almost no difference. This is true in the frame images and also in the simulated wake fields. Experimentally, the shift that we're talking about here, it's just a few femtoseconds. So it's not quite, it's kind of at the limit of the resolution of this technique. And so we weren't able to resolve it cleanly. We hope that maybe if we take a longer nozzle and we just exaggerate this effect, we'll be able to actually directly show this shift. But it's not something that we're able to kind of confidently show with our current experimental setup because our jitter was about the size of this effect. Other things that we were able to start seeing were some exotic behaviors. For example, the mixing of linear and nonlinear fields. What I mean by that is we took a peak simulation, we took the fields from our peak simulation, and we compared them to a linear solution just obtained by solving an integral. And here we have the transverse field, and we take a transverse slice. And if we compare them, we see that on axis, there's a strong deviation between the linear and the peak simulation, but off axis, they match pretty perfectly. So we have the presence of both linear and nonlinear behavior. And the same is true of the longitudinal fields. If we take the off-axis slices, the blue and the orange, we see that they match perfectly. But if we take the on-axis slices, the green and the purple, we see that they deviate significantly. And this is very different than if we take the same parameters and we just add a parabola. There we have a constantly nonlinear field. And if we were to lower the laser parameters to the point of linearity, we'd have a constantly linear field, but we wouldn't have this presence of linear and nonlinear at the same time. That's really a characteristic of these kind of flying focus wake fields. And what you see also is just how much richer and more complex the field structure is inside of the axi-parabola focused field versus the standard parabola focused wake field. We're also able to start probing things like what's the effect of the density on the actual wake field structure, because density is a critical parameter here. And we're able to see that as we ramp up the density, we actually have a very significant shift. The on-axis wake field becomes stronger relative to the off-axis wake fields, and also even normalized to the kind of background field, we have a more and more nonlinear wake field as we go to higher densities. So all of these are just increasing our understanding of how this kind of new creature known as the structured light or flying focus wake field behaves, and allowing us to start learning how to optimize it. So now that we took both our ability to manipulate the velocity and the increased understanding that we developed from the frame images, we wanted to actually see whether we can accelerate electrons. And again, I want to emphasize that with all of the mess that we've seen so far, it's not actually clear that we'll maintain the stability and the coherent structures necessary for relativistic electron acceleration. So the experimental setup here was take our axi-parabola, focus on a gas jet, hope that we get an electron bunch and that we see something in our spectrometer. We were also sensitive to a potential criticism because we wanted to not only accelerate electrons, but also see whether changing the Wakefield propagation velocity would have an effect on the maximum electron energy that we can see. And a potential criticism is maybe as we change the pulse run curvature of our beam, we also parasitically are changing other parameters that would affect the laser fluence. And so maybe the effect that we see would be a result of different laser fluence and not actually of the different propagation velocity. So what we did is we did a fine focal spot scan, and from that we generated a 3D fluence map, and this is a 2D XZ cut of that fluence map. And we did it for the 3 pulse run curvatures that we used in this experiment, as well as for the simulations. And what you can see here is that they're basically identical. So we can be pretty confident that we're actually not changing the laser fluence in any way, and that if we see an effect on the electron energy, it's really from the change in the spatiotemporal couplings and the velocity of the wakefield. So here are the results. So first of all, the good news is that we were able to accelerate relativistic electrons to hundreds of MeV using this technique. And we did it for different pulse run curvatures. So this is the result for the fastest wakefield, for the intermediate wakefield, and for the slowest wakefield. The solid lines are the average spectra, and then the shaded area is the shot-to-shot fluctuation. And if you overlap the average spectra, you can see very, very clearly that there's a strong effect of the wakefield velocity on the electron spectra on the maximum cutoff energy. So we have about a 50 to 60 MeV difference between the fastest wakefield and the slowest wakefield. And if we recreate this with simulations, we get something similar. Now, I will definitely add the disclaimer that simulations have significantly higher charge and also a somewhat higher cutoff energy. That can be explained by the fact that in the simulations, we're using an aberration-free axiparabola, but obviously in reality, we don't have an aberration-free one. And also in the simulations, we're using a more idealized gas profile, so we're losing a lot less electrons. But if you look at the difference in cutoff energy between the fastest and the slowest wakefield, then that 50 to 60 MeV is almost perfectly preserved. Another way of looking at the same data is if we were to just take the maximum cutoff energy for each shot. These are the distributions, and the dotted lines give you the averaged maximum cutoff energy. Now, one thing is that you can actually statistically compare these results, and you see that actually there's a 3.5 sigma significance between the blue and the green distributions, and an even more between blue and the orange. So we see that there is a statistically significant effect of the maximum cutoff energy on from the wakefield velocity. Now, another potential criticism is that maybe there's some sort of beam loading or something like that, so some sort of charge effect that would mean that that would explain this energy difference, and that it's not actually an effect of the propagation velocity. Well, they always say that turn your bugs into features. So there's a feature that actually the charge was all over the place and very, very unstable. But the effect that we saw on the higher cutoff energy was consistent throughout all these different charge regimes. So we can be confident that it's not an effect of the charge, it's not an effect of the beam loading, it really is, and as we showed before, also not of a change of the fluence of the laser, but really of the change in the pulse run curvature of the beam. So that's kind of what we've done to date. And I'll just summarize, I also wanted to show that the nice thing about simulations is that we can actually see what's going on inside of the wakefield. And when we compare on the top the negative pulse run curvature and on the bottom the positive, we actually, the solid lines here are the electric fields inside of the wakefield. And what we can actually see is that in the negative pulse run curvature, the electrons are actually somewhat further away from the 0 point of the wakefield, meaning they're actually somewhat less close to dephasing than in the negative pulse run curvature. So this is a direct evidence of the partial mitigation of dephasing. Of course, this is only partial, by changing the propagation velocity. So just to give a kind of a brief summary of up until this point before we do the switch to the new measurement technique. We've experimentally demonstrated that we can tune the propagation velocity in vacuum using maxi parabola and spatiotemporal couplings. We've used our FREM probe to probe the structure of our new wake field, and we've used that to provide some new insights into this structured light or flying focus regime, like how it behaves when we change the velocity, like how it behaves with change in density, and the mixing of the linear and nonlinear fields. We've experimentally demonstrated that we can actually accelerate electrons, and we've also demonstrated an energy dependence on the wake field velocity with direct evidence of the partial mitigation of dephasing. What haven't we done? We haven't actually shown that this idea really works. What do I mean by that? Is that the electron, and I'm kind of putting the cards on the table, the electron energy that we get with the fastest wake field is lower than the electron energy that we would get using our laser and accelerating with just a regular parabola. So that's not that surprising because we haven't really optimized that much. And also the regime that the axi-parabola performs best in is with a very, very short pulse. So now we're setting up experiments that in the next few months we hope that will really show a significant energy gain. And we have reason to hope that we can actually show that this idea can give a several-fold increase of the maximum achievable electron energy versus just using a standard parabola. But I just do want to say that while we've shown a lot of work towards dephasingless laser wave field acceleration, we haven't actually yet shown that you can get a global energy gain. Locally, we've shown that with the same setup, a faster wake field velocity will give you better electrons than a slower one, but not that we have this global energy gain. But we hope that within the next few months, that will be something that we'll be able to demonstrate. Now, I wanted to just talk about one of the tools that will allow us to also get better control over our spatiotemporal couplings by increasing our measurement capabilities. And this is a technique which was developed with Slava Smartsev at the LOA. We were also lucky enough to have it recognized in Optics and Photonics News. And basically, for those who are less familiar, there is a zoo of spatiotemporal coupling measurement devices. I don't know who came up with this unwritten law that it must all be named after animals, but that's the rule and we follow the rules. But they fall into two camps. There's spatially resolved spectral measurements, and then there's spectrally resolved spatial measurements. I really wasn't kidding. They're all named after animals, with few exceptions like InSight. And we stood by the mission, and our Impala measurement, which is an animal and stands for Iterative Multispectral Phase Analysis for Lasers, falls into this latter category of spectrally resolved spatial measurements. And I'll tell you a few kind of thought bubbles that we'll do that allow us to get to Impala, and then I'll say kind of why we're excited about it. So we'll again return to our favorite beamlets from our two-hole mask, and we'll try to understand more deeply what's going on there. So in space-time, this is the actual interference of those two beamlets, and this is the fringe pattern that we see on camera. And the first thing is that this fringe structure has an enormous amount of information. So for example, if we were to compare two beamlets with no delay, with adding a 6 femtosecond delay to one of the beamlets, we actually see a shift in the fringe structure, meaning this information is directly encoded, not as before when we did a delay scan. And so we're, with the delay scan, we're using Fourier transform spectroscopy, but actually it's directly encoded into the fringes themselves. Also, if we add a relative higher order phase, like relative GDD, to one of the beamlets, so now one of the beamlets is longer in time than the other, this would also affect what we see on the camera, meaning also it's encoded into the fringes. Now, since this is a linear measurement, if we add the same phase to both beamlets, then it won't change what we measure. The second thing is that the thing that we're measuring on camera is actually the addition of the, let's say, quasi-monochromatic wavefronts from each of the spectral bands inside of our laser. So we can think of it as, if we can isolate these different spectral bands, combine them together, what we will get is our measured fringe pattern. So the question is, how do you separate this out? And there are a lot of techniques that work exactly this way, But what they do is they introduce optical components like filters or gratings or other things like that in order to actually spatially separate out the spectral information. But the question is, can you do it without introducing expensive and also cumbersome optics into your setup? So we measure our multicolor far field. And then what we realized is that when we Fourier transform this, let's say for the two beamlet example, we get a DC peak and then we get these two streaks. And the reason these streaks are elongated is because the spectral information is actually already separated in the Fourier plane. So the redder information is closer to the DC peak and the bluer information is further from the DC peak. So what happens if we isolate one spectral band and inverse Fourier transform it? Well, what I actually get is I recover the monochromatic contribution, quasi-monochromatic contribution of that spectral band to my measured far field. Essentially, what I've done is I've put a red filter in front of my beam. And now if I want to, for example, I can do a phase retrieval algorithm and recover my beam sampled only at these 2 points for now for that particular spectral band. But the thing is that in the same shot, I could isolate this spectral band and put as if a green filter, and this spectral band and put as if a blue filter. So in one shot, I have essentially taken 3 measurements with 3 different spatial filters, but without any spatial filters and in one measurement. Now, the problem is that so far we've been talking about 2 beamlets, which is only sampling your beam at 2 points, and obviously you want a higher spatial sampling. But very quickly, as you add holes to this mask, you then have overlap in the Fourier plane, because if you have any 2 hole pairs that have a repeated separation spatially and angularly in the mask, you get overlap in the Fourier plane. But what we did is, using our understanding of how these streaks behave, we actually developed a genetic algorithm, which for a given laser parameter set can give you a more optimal hole configuration. So you can actually, for example, add 10 holes to your mask and get actually much less overlap than you had with the 4 holes that I showed before. And so you can minimize the overlap in the Fourier plane using this genetic algorithm and design a mask that's good for your laser system. So we wanted to start implementing this experimentally. And this is the way the experimental setup looks. So you have your short laser pulse, you pass it through the pinhole mask, you focus it by a focusing optic and measure the interference. Now, the magic of the technology is that the focusing optic that you're using is the in situ focusing optic that you already have in your experimental setup. So first of all, it makes it more likely that you correctly capture what's going on experimentally. And second of all, you don't have to introduce cumbersome optics into your setup. And generally, the focal spot measurement device that you're using is also the in situ focal spot measurement device that you already have. So the only thing that you're adding to the setup, as opposed to measurement devices that could cost $50,000, is this pinhole mask, which can be 3D printed or laser cut at your local facility. The actual output that you have from the measurement is this polychromatic far field intensity. And essentially the heavy lifting, instead of optically through experimental setups, is done algorithmically. So you take this polychromatic far field and you Fourier transform it. Again, you have an amplitude and a phase of these streaks. And once again, we have this spatial separation of spectral information. So the redder part of the beam is closer to the DC peak. The bluer part of the beam is further out. We isolate one spectral band, for example, the red band. And here I'll just add that there is kind of, let's say, there is an additional factor that the measurement is quite sensitive to the whole location. And obviously, when you manufacture, it's never perfectly aligned with your design. So we also have a second genetic algorithm here, which takes the streaks, the design of your mask, simulates streaks, then takes the measured streaks and overlaps them. And it gives you, it basically is allowed to slightly perturb the location and size of each of the holes in order to arrive at the best overlap between the experimentally measured streaks and your simulated streaks, so that the mask that you're reconstructing is the closest to the real mask that you constructed. So now that we've isolated our spectral band, we then inverse Fourier transform, we get the monochromatic contribution of that spectral band to the far field. And now we can do a phase retrieval. Now, we didn't take a near field, and we could, but it would add more complication experimentally. So what we can do is actually use the 0-1 mass transmission algorithm. So just 0 where there is no hole, 1 where there is a hole. And again, through our genetic algorithm, this is now closely aligned with the real constructed mask. And then you can use that as the near field. And through something known as compact support, you can actually retrieve your wavefront sampled at the holes of your mask. We also designed the genetic algorithm to allow for a high spatial sampling of the mask because we wanted to allow for several rotations to get a really good even sampling of the beam. So in the genetic algorithm, you can say, I want to rotate it 12 times, so optimize not only for minimal overlap in the Fourier plane, but also for even sampling as I rotate 12 times. So that's, for example, the design of this mask. And then you get, in this case, we use 3 spectral bands. You get your wavefronts resolved at different frequencies. You can then directly extract the spatiotemporal couplings from these wavefronts because when you do a Zernike decomposition, the spectral dependence of the different Zernike values will give you the basic spatiotemporal couplings. So for example, in this case, you see that the X tilt has a strong spectral dependence. So that is in fact pulse front tilt. And to measure this, we wanted to benchmark it. So we actually induced a pulse front tilt by misaligning the compressor gratings. And we were able to, again, extract the values of the pulse front tilt directly from our Zernike decomposition. And we see here is that we benchmarked it versus simulations of the pulse front tilt from Zemax, as well as from our 2-hole measurement device. And we see a very nice alignment, both with the Zemax predictions, the beamlet measurement, and this Impala measurements. We also induced a pulse front curvature in order to benchmark it. So there we focused using a singlet lens to induce pulse front curvature. And what we see here, again, is a good alignment. The 2 relevant values are the defocus and also the primary spherical. There were also a bunch of other aberrations of the beam, but our simulations matched pretty well with our measured defocus and primary spherical aberrations. So we were able to show that this kind of can actually accurately reconstruct spatiotemporal couplings. Now, in addition to that, I will just quickly say that since the publication of the technique, the group of Andreas Stoff together with Slava actually worked on a kind of more advanced version of the technique. And they're saying that the Gershver-Saxton that we're using, so the Impala spatial separation is good, but the Gershver-Saxton, first of all, it gives you the risk of converging to the non-correct answer. And also it just takes a long time. So as you want to move towards a real-time measurement that could work at 1 hertz or even faster, they moved towards this replacing the Gershver-Saxton with a direct linear forward model, and they were able to show very nice results reconstructing both the phase and the amplitude using kind of Impala, but with a linear model rather than with Gershver-Saxton. So that just quickly summarizes it. So basically, we've worked towards dephasingless acceleration. We have some work left to do. And on the way, we've also developed some new tools for allowing us better measurement of spatiotemporal couplings, and that's the Impala. And I want to thank the people at the Weizmann Institute and at the LOA for that contributed to this work, and also just my amazing lab, Professor Malka, and of course all the funding agencies that were involved. And thank you if there are any questions.
Thank you very much, Aaron. That was a very interesting and great talk. So yeah, as I've said, if you've got any questions, please put them into the Q&A. I do have one to kick us off because I usually there's a little bit of a delay as people type away at the end of the presentation. So at the very start of the talk, you talked about the different length scales, and you had this 4-meter scale in mind. In your opinion, how far away are you from something like that? What are the limiting factors to get from where you are to that 4-meter scale?
Okay, so the 4-meter. So first of all, I think we can. So there are a lot of complications. This 4-meter kind of assumes that everything goes perfectly, but again, as we've gone further along from the publication of these initial theory papers, it turns out that the reality is much messier. For example, the ionization effects and all kinds of things like that. It's also probably harder and harder as you go to even higher power lasers with larger. So for now, we're trying to start off small, and show energy gain in a much smaller system. This also assumes, I think, something like a 15 femtosecond laser pulse. So again, with the accelerators, the idea here is that generally, when you want to go to high energy electrons, like with these results, you want to, because of dephasing, you want to lower your plasma density. Then you need, because you're also lowering your driving field, you then need a longer acceleration length. The accelerators method basically says if you can mitigate that, the regime that you actually work optimally in is going to a very dense plasma and having a shorter acceleration length, but with very, very high acceleration gradients. And for that, you want to match that to a shorter laser pulse. So there's kind of a nonlinear scaling of improvement with the shorter laser pulse, which is one of the challenges that we had kind of demonstrating energy gain so far, because our laser pulse is a little bit too long. So to go to the lasers that you would need to get to these tera electron volts, you need a very, very powerful laser. You'd also need to make it shorter than 30 femtoseconds, which is a challenge. There are these like compression techniques in fused silica, but they've been, they haven't been perfected to the point where they'll be very stable and be able to operate on a 10 or 50 petawatt laser system. So all of that needs to be developed, which is why I tried to be conservative and say, let's say 2 decades. But at least to me, these challenges seem, if you can get this working, these challenges seem easier to overcome than to say, okay, now you have 200 meters of plasma that you have to go through. There are also other options I didn't mention. There's multi-stage laser wakefield accelerators, but each of these has significant challenges to really scale up. And so to me, if we can get this working, the rest of the challenges for scaling up are less daunting than in some of the other techniques.
Great. Okay, we have a question from the audience. Well, 2 questions from apologies if I pronounce your name incorrectly, Chaitanya Varma. So the first one is, FREM, how do you decide where to put the YAG screen to measure the best focused electron diffraction?
Okay, so there's the FREM. Experimentally, it's a pretty challenging technique to implement, and basically the screen, you want it to be very close to the wakefield that you're probing, because otherwise you start having kind of crossing of electron paths, and it becomes much more smeared and also more difficult to reconstruct. So you want the FREM, we kind of try to put it as close to the wakefield as experimentally feasible. We also have to shield the YAG screen because of like laser light that gets through. So we put a kind of a metal plate in front of it, which steadily gets burnt. But yeah, we try to generally put the YAG screen as close to the wakefield as possible in order to kind of accurately reconstruct the image.
Great. And the second question is, given the range of plasma density one scans during an experiment and the range of PFC you can scan, how long does it take to find sweet spots of electron acceleration during an experiment?
Okay, so the PFC system that we designed, it's very easy to change because you just have to, we have a motor with this doublet and you just have to move it. I will say that the dynamic range that it afforded in that experiment was not as big as what we would want. So we want to probably redesign. And also, there are a lot of labs that are afraid of putting refractive systems. There's also the Rochester teams, which are kind of leaders also in this Dephasingless or flying focus laser wavefield acceleration. What they use is an echelon mirror. The echelon mirror, what's nice about it is that it more precisely gives you can kind of exactly encode the right radially dependent delay that you want. The challenge with it is, first of all, you don't have any kind of dynamic ability to change it. And also they're very, very difficult to construct because you really need these very, very small steps that are very sharp. But what we want to then design is something that's more complex First of all, it doesn't just give us a pulse run curvature, but also higher order radially dependent terms, because we want a little bit more control over exactly how the laser flies and not just parabolic. And in addition to that, we want to have more dynamic range. So for that, we're going to have to switch to different doublets than the one that we used. But in the experiments, once it's in place, you can relatively easily move it. So it just takes as long as moving a mirror and then scanning all the parameters that you want to scan. And the same with density for us. It's the challenge is that I would say actually experimentally it's easy to probe, except for the fact that you have a fixed axis parabola and a fixed doublet. And so you need to design those and order them and manufacture them, and that takes a long time. Simulations wise, it's actually more challenging because each of these simulations is relatively heavy, because you have a very long longitudinal window that you want to look at. And also, since you want to capture the way that the rings focus down and when they start ionizing in order to really get the timing between the rings correct, you also need to have a transverse large box. So each of these simulations is relatively heavy, and so it becomes a challenge if you have so many parameters like different spatiotemporal phases and also different focal lengths of your axis parabola and all kinds of different things like that, and densities, and it becomes kind of a challenging multi-parameter optimization problem. So actually the scalability of of probing is, let's say, harder in the simulations.
Great, thank you. I have another question for you. I think it was maybe your next slide where you showed the fields, the acceleration fields. Yes. So particularly the bottom right plot you have here, do you see electron capture within these sort of side buckets that you have, or do you maintain the capture in that central bucket, and does that then affect the downstream electron quality, if you like, that the emittance or whatever, however you would characterize it?
So okay, in this particular case, I will actually say that the density here. So when we were doing this FREM probe, what we wanted to do was really isolate the structure itself and not have kind of charge effects on the bubble. So the density here is very low, so it's 5×10⁻17. So you don't really have injection here just because the density is very, very low. And then as you go to higher densities, you do see some, but also the central wakefield becomes more dominant over the radially offset wakefields. So it becomes actually less kind of a feature.
Okay, so then it doesn't actually impact the
yeah, but I will say that on our spectrometer, I'm not sure, like in the simulations we can see, but on this experimentally, this would be, I guess, an interesting thing to examine. I'm not sure that we can really, because we have some divergence, which is probably larger than the spatial difference between them. I'm not sure that we can resolve this, but it would be an interesting thing to be able to examine.
Thank you. I think we've just about come towards the end of our time. Well, we've come past the end of the time slot, but our new time slot.
Sorry again for the
it's
technical challenges.
These things happen. So what I would say is thank you once again for the presentation, and it was very interesting. I hope everyone enjoyed it. The presentation will be available on YouTube after this, so if there's anything you want to skip back through and watch again, feel free to have a look there. And I suppose if you have anything more pressing questions, you can reach out to Aaron directly. And yeah, thank you once again. Thank you for joining.
Thank you very much.
Yeah, great. Goodbye, everyone.